Normally I'd have a slide deck to present. I decided not to this time. Just gonna kind of talk through the agenda. So as you all know, this is gonna be Monday through Thursday of this week, 9 to 11 a.m. most days, except for tomorrow, Wednesday, when we will end 1 hour early for the general PyHC public, if you will. We're going to be doing some usability testing for the HSSI. Jenny Knuth is leading that effort, and just a few of us who are involved with the development will be sitting in as kind of silent outside observers. I'm sure we're going to be doing more rounds of the usability testing. So if you're interested in being involved in that, let us know. By us, I would mean me or Rebecca or Sean's a great option as well. And we'll try to get you in for the next round. Right. As for today, we're gonna have some project updates as well as Nick at the end of the call today, giving us a tutorial on using UV to create virtual environments instead of Python projects. Tomorrow, we're going to be talking about S3 awareness in PySpeedas with Jim Lewis, and then Sandy Antons is going to talk us through Cloud Catalog for Cloud and laptop use. A bit of a follow-on from the telecon if you were there. Gosh, I forget what was that, a month or two ago at this point. Wednesday is sorry, it wasn't Wednesday that we ended early. It's Thursday. My bad. I looked at the schedule wrong just now. But it'll be going through the HSSI a little bit, a quick update presentation, and then a vocabulary working session where we're going to get feedback from you all on some of the vocab we're using. And then finally on Friday, well, I'm getting my days mixed up. It is Wednesday, we ended early. On Friday, we're going to be doing a discussion on DOI minting and best practices, talk through some FEB updates, and John Mehoff has a lot of comments on that for y'all. Do a revisit of the PyHC user survey, and then so that's what we got coming in the future. I don't want to steal too much time from the people who are actually giving cool presentations today. So let's see, we have Bob Weigel on. Awesome. I believe you're up first with a happy update. I'll put the agenda link in the chat as well.
Okay, I think I'm ready to go. All right, feel free to just jump in anytime during the presentation. If you have questions, I have about 10 minutes worth of discussion here. And let me get started. So this presentation is on HAPI, which is the heliophysics application programming interface. It's a little bit different than some of the other presentations that you'll hear today, in the sense that this isn't strictly a single Python package or single Python project, but it's used quite a bit in the Python world, and there is a Python package associated with the project. And so I'll start out with this outline, scope of the HAPI project. I'll talk about some of the server updates and then some of the client updates and some comments on PyHC that I think are relevant for this forum. And then I'll discuss some of the specification updates and go from there. So the scope of the project is that it's a development of a standard for HTTP endpoints for time series data. So you've probably all dealt with data files and also getting data through an API. So just a web URL that returns a file or a CSV or CDF or FITS or that sort of thing. This is for services or APIs that actually return data. And it also involves the development of a standard for associated metadata that goes with the data and a data streaming format. And we emphasize that what HAPI provides is not a data format. It's really just a streaming format, and it's not expected that users are going to be looking at that data stream, even though it's a simple data stream that is interpretable by humans. Another thing we do is we work with server developers to add HAPI endpoints to existing services, to create new HAPI servers. And we do outreach to get more data available through the standard. We've also developed some generic servers and clients, the Python client being one of them. Okay, and then we also have an increasing demand for the ability to search happy data. As it is now, if you know what you're looking for, it's pretty easy to get at the data. But then the question is if you don't quite know what you were looking for, how do you get at it? And we've sort of set a boundary for this project and said that we're going to avoid doing the search side of metadata and that the search part will be left to SPAYS. And that's just something that comes up somewhat often. And I'll give a few updates on the servers. The CETA was one of the very first servers. It's pretty limited in terms of its metadata and in terms of its total coverage of CETA. There's some data sets that aren't quite working. There's been a recent rewrite in Java by Jeremy Faden that's in progress, and I have a link here to a development server on his development machine back at the University of Iowa, and we expect that release to be in the summer. It's undergone very thorough testing, pretty much every data set, checking to see that the clients can read from it and plot data from it. And we've also made it backwards compatible. So if you have URLs, happy URLs in your scripts that read data, they should just work. We've made significant improvements to the metadata so that all of the master CDF and so-called all.xml, which is higher level information about CETA data sets, is included in the happy metadata. Happy metadata tends to be limited to metadata that you need to create a scientifically sensible plot, and then additional things for like search and detailed documentation. We provide pointers to that. And we've also added support for, or we will eventually add support for time varying support variables. In CETA or in CDF files, there's two types of variables, data and support variables. And sometimes people want to look at both of them. And so you'll have that ability to do that. And in the past year or two, the World Data Center at Edinburgh has modified their existing API, which produced JSON and some flavor of CSV. And they've modified their server that was Python Fast API and essentially created happy endpoints for it. And so all of those data are available. And that's, yeah, 5,000 data sets. Intermagnet also has about 3,000 data sets. Their data sets go from about 1990 to present, whereas the World Data Center goes back all the way to the very beginning, around 1900. And they did something similar. They had an in-house Java-based server for their API, and they added happy support fairly quickly. And then within the past few weeks, we have a working version of SuperMag, which has 601 data sets that are primarily 1-minute data sets, and I think they're planning to add 1-second cadence data sets. And they're different from the Intermagnet World Data Center in the sense that they also have custom indices, and they include some interplanetary magnetic field measurements. And then we have CCMC. They have 300 data sets. They've been going for about 5 years now, and we've been in discussion with them because they have an API for their CAML tool, which is used for analysis of predictive models. And like many of these systems, they have their own API, and it maps pretty cleanly to what Happy is doing. And so we're trying to discuss how to get that moving so that more data is available through the single interface. And if you want to get data from 3 providers, you don't need to download 3 different clients. And then they're also considering adding simulation-derived time series, so like fly-throughs of the magnetosphere. Client updates. These are several clients. We have an online client, which is the so-called Data Explorer. I'll just flip over to that real quick. Maybe. It's at happyserver.org/servers. And this is an interface where you can browse through all of the available servers. And so You go to SSC Web, and we've recently added a bunch of features. So if you haven't been here in a while, you can have a look. We've added time range coverage, so you can look at, I'll open this in a new tab. You can look at the coverage of available data for each of these data sets. And there's also the interface was one of the primary goals of the interface was to get you moving on the data pretty quickly. And so there are options for generating scripts to download a given data set, whatever's selected here, in various different libraries. And so we have Python SpeedOS, and then two different versions of Komodo, two different examples of doing it with Komodo. And so this script is auto-generated, and it's essentially, uh, 5 or 6 lines of code. And then we also have an example of doing plotting. Uh, how much time do I have, Julie?
You have about 2-ish minutes remaining.
Okay, got my timer flipped over here. All right, and so I'll just go back to the Python thing. The the primary interface is the happy client, and that's been stable for some time now. We're considering separating out the time handling into a standalone library. Some of the people that have Python servers, they do their own handling of time, that get passed through the URL, and they, read the specification and come up with their own time parsing and error messaging. And I think it might be a little bit cleaner if we provide them access to just that time handling part as a standalone. We've added support for people that have to access data through a proxy, and this thing is pretty old, and the interface is not quite Pythonic, and there haven't been many complaints because most people just wrap it and make it consistent with however their interface works for data access. But there's still some weirdness in there, just owing to the how it was developed initially, and that we plan on modifying and making it more consistent with how people do things in Python. Um, the plotting software. So if you go to this Happy server, there's the Happy client, and then you can also generate a plot. And this backend plotting library is an optional thing. And there's been some demand for a little bit more flexibility. So it was sort of developed just to create a quick look plot. And we're also in discussions of separating out some pieces that are fairly mature and don't really need to be buried within a single package. It has to do with the date labeling, which is always a problem in Python because the defaults are terrible. And then also generating a heat map and dealing with gaps and missing data and that sort of thing. And so we'll probably split that out into its own different package. And then this I can skip, and then I'll jump to some updates on the specification. We've added the ability to specify the location and geolocation of a data set, and that's primarily for ground magnetometers, but it's also location can be a generic thing. It doesn't have to be necessarily a ground magnetometer. And we've added some features to allow people to make their happy data fair, warnings and notes. And then we've also added max request duration because with Happy, you can just request, a data over a 20-year time period, and the server might not be able to handle it. And having the client and server negotiate, or the client having to figure out what the max duration is not very efficient. So we allow Happy servers to provide that information for the clients. Okay, that's all I have. Thank you.
Great. Thanks, Bob. Anyone have a quick question?
I have a quick little comment.
Sure.
On your the web interface that you have, I just wanted to say that's a great way of doing it, where you can go in and just say, okay, I want to look at this data. Give me a little snippet of code. So props for that one. That's really great. I hadn't
Yeah.
seen it yet.
Okay, thank you.
I was also going to say that, and the addition of the timeline was really good. Was that fairly recent? I hadn't seen that timeline thing before either.
Yeah, that was within the past month or so. That was actually a PyHC summer school homework problem that I just copied over.
That's
So
awesome.
yeah.
And quick question, kind of unrelated, but Has Doug Lindholm always been in your author list, or did you recently collaborate with him and then add him to that?
He's been he's been with us sort of in the beginning and sort of a prototype of this. I had worked with him on a proposal many years ago, and he comes and goes.
Okay,
So
cool. I was just curious. I wasn't used to seeing his name there. Thank you.
mhm.
Awesome. Well, thanks again, Bob, for the update. Go ahead and get moving to the next one. I see Stuart, you already have your camera flipped off. Perfect. Next up is Senpai.
I seem to have lost the tab with my slides in it. 1 second. I have too many tabs. Is that behaving itself? Okay, this is just a quick roundup of everything that's happened in the SunPy project since like the last PyHC meeting in November-ish. That's so many levels of the wrong. Oh no, let's try that again. We've had quite a few releases in our various packages in the last 6 months or so. SunPy 7.0 was supposed to be out at the end of last week, but got delayed by a week to cram in an extra bonus fun feature. So we should have that out this week. We had a major release of NDCube, Sunkit Image, Sunkit Instruments, DRMS and MagX, and a couple of other little releases of other things. For those of you who don't know, the SunPy package and the SunPy project, two subtly different things in that the SunPy project has lots of packages that we look after. These are some, but not all of them. Some of them are quite quiet. Okay, so highlights in the core package itself. I've taken this out of the what's new section of our documentation. So if you want more information, you can go and have a look at that. First thing in 6.1 was adding the ability to plot the edges of images on other images. So in this case on the left, this is like you take a submap and then you can plot the bounding box of the submap on the map it came from, but you can also plot the field of view of another instrument. I think in this case it's EUI, high-res EUI, which is on Solar Orbiter, so it's a very different. Oh no, that's EUVA, so that's probably plotting something at Earth on a stereo image. It's probably the same rectangle. It's probably plotting this rectangle as seen from stereo. There we go. The dotted lines are behind the disk, like the other side of the sun from the direction you're looking at it. That was primarily done by Will. The other thing that hit 6.1, which has been on the to-do list for a very long time, was adding helioprojective radial coordinates. I won't go into the details too much, but the common coordinate system that you can see here is helioprojective Cartesian, although it's a spherical coordinate system. Don't let names confuse you. And helioprojective radial is the same coordinate system, except it has the south pole of the sphere at the sun center rather than the 0, 0 line of latitude, longitude. So you have these nice coordinates that move away radially from the sun. You can also reproject into that coordinate system to flatten the sun out. So there you go, you can have a nice flat sun. That was the other big thing that ended up in 6.1 was initial support for S3 URIs using FSpec. Almost everything apart from CDF files just use the standard FSpec path code. So if you've got your data on some other cloud provider or in fact anywhere else, you can use a lot of the other FSpec plugins, not just the S3 one, but this is a example of loading map from an S3 URL. Also supports in time series for many different things. These things are coming up in 7.1. We added support for two relatively new observatories, which is Punch that launched earlier this year, I think, and Suit, which is on an Indian satellite at L1. Also added support for the newly generated level 1 EIT data on SOHO and Gong magnetograms. So always nice to add more data. Our auto-align plotting for map got big upgrades, both in terms of speed and functionality. So you can now plot, you can auto-align by mesh, or you can auto-align by image. And if you leave it as auto-align true, which is now the default, it will just pick whichever one is the best one. Image being faster than mesh, but not always working. The cheeky thing that got snuck in under the deadline was the ability to warp off-disk points based on the rotation of the sun. This one is relatively complex to explain, but if you are doing coordinate transforms for points off the actual assumed sphere of the sun, you have to make assumptions about where they are in distance away from the observer. And one of the things you can do is assume a screen of constant radius. You can now warp that screen based on differential rotation of the sun, so you can see that the area around the equator has been warped more than the areas around the pole of the screen. This has been something that Albert's been thinking about for years and has finally come up with a solution. They're the big things in 6.1 and 7, although there are more. You can go and read about it in the respective What's News, as I said earlier. NDQ 2.3 came out earlier in the year. It adds ND meta class. The big functionality in that is that you can assign metadata to an axis. So if your exposure time varies with time, you can set an array of exposure times along one of the axes and say that this piece of metadata is attached to this axis, and then if you slice your data in a certain way, that metadata will also get changed or adapted. We added a squeeze method, a la NumPy squeeze, to remove length 1 axes. There was a significant performance enhancement in axis world coords, which was a collaboration between about 3 people in 3 different pull requests that slowly made it faster and faster. But it is now massively quicker by removing redundant computations. And we added a nice little -1 shortcut to rebin. You can see the changelog in the ND cube docs. Sunkit Magex, for those of you who don't know, is the spiritual successor to the PFSS project. After that was archived by David, SunPy picked it up, breathed some life into it, and called it Sunkit Magex. The idea being we'll eventually add other extrapolation methods to it. Along with that came the Stream Tracer package, which is a fast library for doing stream tracing in Python, which is written in Rust and has been significantly. It used to be written in Fortran, is now written in Rust, and has had some significant performance improvements added to it in the last couple of years. So it's now significantly faster than the old Python Fortran version as well. Sunkit Instruments had things added for DEMs and temperature response, as well as some extra sous vide, sous vide being a GOES instrument, and a few other bits. I thought there was more. No, okay. And finally, our coordination meeting is in London in a few weeks' time. Remote participation is encouraged. If you're interested in joining us, please go to the SunPy website and have a look at the details and register. That's everything.
Great. Thanks, Stuart. Do we have a quick question or two for Stuart?
Stunned silence. That's what I like to say.
It's just the updates are so amazing. They don't know what to do with themselves.
I'm just curious, how does that auto alignment of plotting maps work? That seemed pretty fancy.
It uses Matplotlib to greater or lesser extent. There's two ways it does it. It either does it by creating a Matplotlib transform and then calling imshow so that Matplotlib transforms the image into the target space. That works fine for most situations unless some of the edges don't transform properly, depending on what your two maps are. If you've got a map which is like round the back of the sun and you try and plot it on one which isn't, it can get very confused when some of the pixels resolve to nan in the destination coordinate space. And the other one is using Matplotlib's P color mesh, where it draws a polygon for every pixel.
Okay.
Um,
and in
that
that
the P
situation,
color mesh functionality has existed for a while, but we sped it up a lot by pre-computing the transform and doing a few other clever things.
cool.
Great. Oh, go ahead, Ken.
Just following up on that, does that actually create a new array and
No, it's
cube
done
with those?
dynamically at plotting time.
It's just a plot. Is
Right.
there a way to get those remapped arrays?
Yeah, you can use the reproject2 method if you want to generate a new image, which uses different methods for doing it, which are probably
Okay.
better if you care
I see.
about arrays.
Thanks.
Thanks again, Stuart. When you get a chance, if you could put your slides in the drive, that'd be great.
Mhm.
And next up we have Darren. Is it Chaddock or Chaddock?
Either, yeah, Chaddock, you avoid the photonic Chaddock, but everybody just says it faster, so sometimes it's Chaddock.
Fair enough, fair enough.
All
All
good.
right.
Okay, I'm gonna share. All right. Great. Is that full screen for everybody? Yeah, okay.
Sure is, yeah.
Okay, great. All right, I'm Darren Chaddock from University of Calgary. So a little bit new to this scene. I haven't been to one of these meetings yet, but some of you probably have seen me at other meetings. So I'll talk a little bit about what we do at the U of C with primarily it's all sky imager data, and we have an open data platform with a couple different tools and websites and such. So I'll go through a little bit of an intro about what the data is. Most people are probably familiar with Themis ASI. Yeah, most people are probably familiar with Themis ASI. It's been around since 2005 range, and it still goes. I'm a little surprised that they're still running. But we're now at about 120 terabytes, 400 plus referee publications. It's been pretty impactful. So if we move on, more recent stuff, T-Rex RGB, Transition Region Explorer is what T-Rex stands for. And these are full color cameras. Those have been running since 2018. COVID kind of put us back a little bit with getting most of them in the field, but we had a few back then. We're about 120 terabytes now for that data set alone. The RGB side of it, it adds up pretty quickly. If we take a picture of everything that we have, well, not everything, but the majority of what we have, this table is showing on the top GDCG, which is a new project I'll talk about hopefully at the end. Themis or Smile ASI is the replacement for Themis. It's full color cameras, and we have 3 of them in the field. And I think by the end of this year, we'll probably have 10. We'll see how the summer goes. Themis ASI, again, 2004 range. T-Rex has a couple different cameras, blue line, NIR, near infrared, and full color cameras. We also have some spectrographs, and the list kind of goes on and on and on. So I guess the point of this one is that there's a lot of diversity in here, building tools to manage all of this instead of just one type of data. I think we're all familiar with with that kind of situation. So PyAurora X, where does it fit in this picture? I'm just moving my little screen here for the video so it doesn't cover. Okay, yeah, so where does it fit in? So Aurora X data platform is a project that we had starting in 2020, I think. It's Canadian Foundation for Innovation project that was funded to develop tools for accessing and exploiting the world's all-sky imagery data. Since we have a good chunk of it, it first got populated with a lot of our stuff, and we've been slowly adding other people's things, and it just keeps growing. So what does the whole platform include? It includes data access and analysis support tools like for PyAurora X. It's also got an IDL version. We have web visualizations and summary data browsing tools, ways to quickly get into the data, figure out what you're actually interested in. And then you can go and use the tooling like PyAurora X to dive into the raw data and start making plots for papers and going down that rabbit hole. We also have conjunction and ephemeris search engines. These have some machine learning integrations into them to enrich that metadata to make it a bit more effective. So PyAurora X, what can it do? We can download data, both raw and summary data. For currently, it's MSASI, RGB, near infrared, blue line, the spectrographs, and RIGO, which is a red line camera, or an array of red line cameras. We can read the raw data, and we provide a lot of common analysis functions for people. Meanwhile, we also expose the raw data, like the actual information that's going into those functions, for people to go and do whatever they want with it. We're not there to make functions for every single thing you could possibly think of. We want to provide some basic tools, basic ways to get into it, and off to the races you go. Performing conjunction searches and ephemeris searches, that can also be done with PyAurora X. We can filter those searches on machine learning models that we have. We also have the Transition Region Explorer Auroral Transport model. This is a model by Jun Liang here at the U of C. He's been working on this model for a good chunk of time. I won't go into it. I don't know the details for the most part, but I'll leave the documentation pages for that. So whenever I talk about our data, I usually broadcast saying to go to our open data platform. This is the starting point of everything. This website shows how to get to our data, how to use our tooling. Next slide here. So this is the big list of all the examples. So for PyAurora X, you can do all sorts of things like I've shown, or I will show. And this list is just a quick snapping to each of those examples. So into some examples of things, listing data sets. Each of the data sets has built into it the DOI. If we've created one, we're trying to get more and more of them created. I think it's around half or so. And so each of the data sets has those pieces of information, contact details, where the tree is, some descriptions, things like that. When it comes to the analysis side of things, keyograms. Keyograms are a good way of looking at imager data, all sky imager data, without having to look at movies every night. I think of them as a 2D time lapse. So on the bottom axis is time, and then on the y-axis is can be a few different things. In this case, it's just CCD coordinates. So looking at this keygram, I see substorm onset later in the night, just around here, and I also see pulsating aurora, which are these straight lines all below. So you can see quite a bit from keyograms. You can also look at the raw image, like just a single image. You can make a movie of single images. There's some utility functions there to help make movies. Again, keygrams. This one has on the side magnetic latitude, so you can map these to magnetic coordinates using our sky maps. Examples. All of these figures are actually taken from those crib sheets that I showed a couple slides ago. I just copy pasted them. Montages, we can make these kinds of figures. So instead of a keyogram to show the temporal side of it, you can look at little thumbnails of each one. You can change how much data goes into this, how many, like the interval of it. Maybe you want an image every minute, something like that. You can also put contours on top of images. In this case, I think that's geodetic contours of lat long lines. It might be magnetic. I don't think it's magnetic. Then you can also say, okay, I'm kind of interested in this region out that, of the image. Maybe I want to see what the counts are, what the imager saw over the course of an hour. So you can pick out a bounding box, and then it shows you a plot of the data over that period of time that you pass in. Then putting things on maps. This is a bit of a tricky part, but we've been doing it for a while, so we know the pitfalls here. And so we can stick RGB cameras on a plot or on a map. There's a few of them here. So there's how many? One, two. There's 5 of them here. Then we can also do a bit more complex where we're mixing instruments. So we have RGB on this kind of side and down below, and inside the middle here we have Themis ASI. And then on this side we have a redline camera. So we can stitch multiple cameras together like this. You can also do the same kind of thing where you have a mosaic with some satellite traces on them where the footprints are of spacecrafts. Another example is RGB with our spectrographs laid over top. Spectrograph is it's similar to an all sky imager, except it takes a single slice of the meridian, and then you get the depth of it actually in wavelengths. So it's around 400 to 800 nanometers, and you can pick out whichever band you're interested in. You can plot that over. So quickly about our higher level data products. These are products that we're working towards. We've started on them where it's a standardized grid. We're trying to making mosaics. It's computationally intensive, and it can be a bit tricky to know how you want to overlay them. And so what we've done is we've created a higher level data product that is these grid files that we've already made the mosaic for you. We've chosen for this period or this timestamp which cameras should be showing. Maybe one's cloudy, maybe one's another has some snow on the dome. It happens. And so we go through and we remove that. And we say, okay, you're looking at Aurora when you're looking at these keygrams. Or sorry, not these keygrams, but these grid files. But what comes with that is you lose some resolution. Just because we're fitting it to a smaller grid. We've picked the NOAA grid that they had a few years ago. They've kind of gone down in size since then, but it seems to be working out. It's about 0.3 degrees latitude and longitude for each pixel. ATM. So some of the things you can do with that, you can get volume emission rates. That's on the side here of different wavelengths. You can also get ionization rate, temperatures, plasma density. You can also make conductance maps out of it. And Jun just keeps adding more and more stuff. I can't keep up with him. So when it comes to conjunction searching, how didn't start my timer. Am I okay on time here?
Let's see. Sorry, just trying to find my microphone.
Yeah, okay.
I believe you have we started a couple minutes late because we were running over on the other things. So 7-ish minutes.
Yeah. Okay. All right. Great. Perfect. Excellent.
Yeah.
Okay. Yeah. So conjunction searching, you can do this within PyRX. So this example is we're going to say, I want to find all conjunctions for a month of time. So January 2008. I want to find them using the North B trace, like the northern magnetic footprints. I want to say there's a distance of 500 kilometers. So from any ground-based instrument or really any other space-based, you want to say a 500 meter or 500 kilometer radius around there. Anything that comes in that range, we would say is a conjunction. You can say, okay, maybe I want something that's kind of closer to the site, 200 kilometers, or maybe I'm not too concerned about it. So maybe we go 1,000 kilometers, just something that's in the vicinity. Then we say, okay, ground criteria. So I'm saying I want to find all the conjunctions in that period of time for any Themis camera, any Themis ASI camera, and any Themis spacecraft when it's in the Northern Hemisphere. And I want to filter those results on any time that our machine learning model thinks that there's amorphous pulsating aurora in the field of view. We can also add some confidence to that. So say, it just only show me times when the model is quite sure of it, 95% confidence. or higher. And then it goes off and it found, in this case, it found eight records. Now, it's hard to visualize this quickly. So this is where the website side of things comes into play. You can do these conjunction searches from the website. This is actually where it began. This was the first thing that we made. So we have a couple different examples up on the top, and I'm just loading example 7, which is this one. So here are the results, the 8 results that we found, and we can actually go into Swarm Aurora, which is another web-based tool, and go through those results. So maybe you're trying to do some conjunction searches on your computer using like a Jupyter Notebook. You can kind of do that search like in the previous slide with the code. And there's actually a function that says to open in Swarm Aurora, and it'll launch your browser, and then you can go in and have a look at those conjunctions. So that's kind of how those two pieces come together. Okay, that's PyAurora X. I'm gonna talk a little bit about the other stuff that we have, because it's just one component. So our open data platform, data.phys, place to go to start to see all the data sets and learn about the resources that we have. We have the data portal, which is a web interface for browsing summary data. Swarm Aurora, that's for finding conjunctions, also looking at summary data. And then the Aurora X data platform, which is the conjunction searching, looking at raw data, and also there are some summary browsers, summary data browsers, a couple different types. We have our tooling, PyAurora X, IDL Aurora X. We have a newer one called PyHC Rio. That's for working with our rheometers. They're quite different. So we have some tools specific for those. And soon we'll have an ideal version of that, I would imagine, by GEM. And then SpeedAS. You can use SpeedAS for viewing or working with the Themis ASI data and also the red lines, but just those two for now. So the website, data.phys, we have dataset descriptions. Each of the descriptions, you can go into these pages and they'll have maps of where the cameras are. There's contact info, DOI on the side. So a lot of this information is similar to what's in the API. Our data is accessible HTTP, FTP, or rsync. You can also get at it using our new API, which is under the hood what powers PyAurora X. You can use the Python tooling. And I encourage you to go to all the examples and sift through those. We also have this visualization. This is part of Aurora X. It's called the Event Explorer. And back November or October last year, we released it to the public. And recently I've been able to get a boatload more data into there. These leverage, what you're seeing here is you're seeing the grid files that I spoke about kind of in action. So under the hood, this is showing those grid files. And on the side, you have keyograms. This is I would say it's pretty similar to Swarm Aurora. It's an evolution of it. Swarm Aurora was a static map when you're looking at conjunctions, but it has the keyograms on the side. So we're working towards polishing this and making the loading of the grid data a little bit faster. So we're always tweaking. Future plans is my second last slide. So we're going to continue working on the API, Python, and IDL tools. The nice thing about this is that since we make the instruments and the data, for as long as we have those instruments to operate, funding to run them, there's going to be support for these tools. It's a package deal. It's our responsibility to make all this data accessible and usable. It's no longer can we just put stuff in a data tree and say that's good enough. So it's baked into our operational funding. We have a new SMILE ASI instrument array, like I was talking about earlier. They will start, I would imagine everything will be probably deployed by the end of next year, but we'll see how it goes. Then GDCG. Okay, last slide, which I find scary, but GDCG is a Canadian Foundation for Innovation project that's been funded. Money started flowing in around November or so last year. And this is to build the next generation of instruments. The goal was that it would support GDC. And we have a couple different types of imagers, instruments actually. It's 134 instruments across 27 sites. The plot on the right here, the blue is anything new, and the yellow is things that exist already. That'll get upgraded. They'll get new instrumentation there. So it's going to be a lot of work. We've already started designing the red line and the RGB cameras and a bit of the GNSS. So we'll just be working on this over the next 5 years. And any data that gets produced from this system will get integrated into PyRX and all of our other platform tools and such. So it'll just hook right in. So yeah, that's pretty much it.
Thanks, Darren. Do we have a quick question for Darren before moving on?
Again, I've wabbed them too much.
You did great. And yeah, good luck with the other work.
Yeah. We'll see how it goes.
Sure, it'll be great. All right, all. Let's see. Next up, we have Nikhil Rao talking to us about GCM Rockbite.
Yep, let me just share my screen. All right, can you guys see my screen?
Yes, we can.
Cool. Well, hello everyone. I'm Nikhil. I'm a software engineer at NCAR. I started there about 1.5 years ago. That's when I started working on this tool. So what is GCM ProcPy? It's a Python package for post-processing and visualizing DiGCM and WACMX model outputs. It facilitates data analysis, plot generation. You can access it with multiple interfaces, GUI, API, or command line as well. You can make plots, movies. It has functions for data parsing and post-processing. And it's compatible with Python 3.8 and above. The motivation behind making GCM ProcPy. So earlier, everyone was using tools like DiGCM IDL and DiGCM ProcF90 for DiGCM and WACMX data processing, which had limited flexibility and like modern data analysis workflows. And new users, postdocs, grad students had a difficult time getting used to those tools. So I built GCM ProcPy on Python using various libraries for a more user-friendly platform and also more versatile. Originally, GCM ProcPy was DiGCM It was initially developed only for DiGCM output. We renamed it to GCM ProcPy to include a WACMX as well. With the renaming, we refactored the entire code, made it modular, added a graphical user interface, and added interactive plotting routines as well. This just goes over the timeline of GCM ProcPy. The first initial release was in October 23, and it was renamed to GCM ProcPy last year, October. And with the latest release, we added the graphical user interface. Now the features, as I said before, there are 3 methods. The GUI, as the picture shows here, you can call it with the function calls, as well as command line calls. There are various things that you can do by ingesting the data. So DiGCM and WACMX have netcdf outputs. So you just parse them in, you have data exploration functions that you can see what the data is about, all the variables that are being calculated. Then you have data manipulation functions that aren't really used by users. It's just the data array generation functions that are calling the data manipulation functions to generate the arrays, add in missing values, and all of that. You have emission calculations functions, and various plotting routines and movie routines. So the various plot types are your basic lat-long plots, pressure level variable plots, pressure level longitude plots, pressure level latitude plots, pressure level versus time, and latitude versus time. The documentation is automated in a way that we use Sphinx Autodoc. So it basically takes in the doc strings from all of the functions and puts them in a good format on read the docs. GCM ProcPy currently uses the Google style doc strings. So I have made GCM ProcPy in such a way that everything is modular in a way that if you could see over here, the movie functions call the plotting functions, which call the data array functions to get the data and plot the movie. So if you want to add a feature on, let's say, lat-long plot, you want to add night shade. So you make the changes to the plotting function and you just add a variable in the movie function. So you won't have to do that many changes to it. I've just highlighted which method of interface each types of function is exposed to. So plotting functions can be used via API, CLI, or GUI. Currently, the movie functions are only available via API or CLI. But yeah, I've built things in such a way that each type of function is contained and callable and is being used by other types of functions. Future development. So to work on building a robust framework, I'll be removing 3.8 and 3.9 Python support because certain things are deprecated and I don't want to make them optional. Adding data exploration functions to CLI and GUI, enable moving routines on GUI, adding polar plots, additional emissions calculations, and I have to do a lot of performance optimization on the data array creation functions. I have a Colab Jupyter Notebook, so anyone can get familiar with how to use the tool, and pretty decent documentation, I'd like to say, on Read the Docs. Currently I am the only developer on this project. If you'd like to contribute, I'd be really grateful. Yeah, I mean, that's about it for GCM ProcPy.
Thank you. We have a bit of time. Do we have any questions? Right. Well, if we have no questions, we'll go ahead and move on. Or if anyone thought of a question from a previous presentation, you can also speak up now. I'll be awkwardly silent for 2 seconds. Okay, cool. Well, thanks again, Nikhil. All right, go ahead. We do have Jim on. Jim, would you like to go ahead and go with your PySpeedos update?
Sure. Let me go ahead and start sharing my screen here. Okay. Okay, so hopefully y'all can see that. So I'm Jim Lewis. I'm the lead developer of PySpeedas, presenting on behalf of the PySpeedas development team. And I'm going to talk about some of our updates since the last PyHC meeting and some things that are coming for the future. One new development, we actually have a new team member, and I believe he's on the Zoom today, Dan Carpenter, and he's just joining us. Today's his first day on the job, and we're fortunate he actually already has some exposure to SpeedS and PySpeedS, and so we're very much looking forward to having him as a contributor moving forward. So welcome, Dan. For the future updates, I want to talk about a lot of these came out of the PyHC summer school last year. And then Vasilis Angelopoulos at UCLA used SpeedS and PySpeedS for one of his data analysis classes at UCLA earlier this year. And that is a fantastic way to get feedback on where your weak points are. Nothing like a highly motivated captive audience to show you what needs to be improved, because believe me, they're not shy about asking for stuff. But yeah, we had an explosion of development around those two events, and made us into much stronger system. So for any other package maintainers, if you can contrive a way to get your package in front of a classroom, that's a fantastic way to see where there's room for improvement. So the first thing I want to mention, this is really sort of a separate thing. PySpeedS now has the ability to load files over from S3 buckets, for example, from HelioCloud. And I'm not going to go into detail. This was developed by Brent Smith, and I believe he has a whole presentation on this tomorrow. So if this is of interest to you, for sure, see his presentation. But in a nutshell, the way PySpeedS is set up to work is you have various data providers that have their own servers. It could be individual missions or CEDA or other archives. And in the PySpeedS load routine, typically you use the time range and the instrument and the data set you're interested in, and you put together a list of URLs where that data should be loaded from, and then you load those files from the remote server to your local machine. And then from there, depending on what type of file it is, use CDF to tplot or netcdf to tplot or some tool like that to load the data from that set of files into tplot variables that you can work with. Now, if you're in a HelioCloud or some other cloud environment, it would be nice if you could skip that step of downloading to the local data directory. And ideally, you would be able to stream the data straight from the S3 buckets into memory, into your tplot variables. So Brent and his collaborators have done exactly that. So that is now available in PySpeedS. And so again, I would suggest checking in on his talk tomorrow if you want to hear more about that, but we're excited about that. So let's see, another area where we've made quite a bit of progress is in plotting. So for some of our plots, we were sort of stuck with the matplotlib defaults for a lot of the plot attributes and styling. And so we've added options now to let you set the different matplotlib options and customize the plots a little bit better. We have a lot of users coming over from IDL SpeedS, and the terminology for how you describe a plot is maybe a little different in between IDL and matplotlib. So to make that transition a little easier for them, we've added a lot of synonyms so they can use like the IDL style option names as well as the matplotlib style names when they're setting up options. We've made some big improvements in composite variables. So this is a feature in SpeedS and PySpeedS where you can store data in a tplot variable by directly specifying a time array and a data array and a metadata dictionary. But sometimes you just want to take some existing tplot variables and combine them onto a single plot. And so in that case, you would, in the store data call, you could just pass a list of variable names, and then it'll know that when you plot that, it should grab the data from each of those individual variables and plot it on a single panel. And that can get a little bit tricky, especially when you're plotting several spectra on the same panel. And I'll show some examples of that. Another feature that had been missing that we now have is a way to do interactive time selections by clicking around on a plot. So you might have a time series plot that might have some interesting features on it, and you might want to record the times of those features and then do some further processing using those timestamps. And now we have a way to do that just by clicking around on the plots. So that's very convenient. Another update I'll show is we had a lot of requests to change how variables get annotated. Like in the plot call, you can pass a list of variables that instead of plotting them, you just like record their values at, say, the different time tick marks and just print them underneath the plot. And that's been available in IDL for a long time. And it was kind of clunky in PySpeedS, but we've made a big improvement. I'll show that. And then another improvement, and this is again coming from by request of some of our IDL users. In IDL, a lot of the utilities could take a wildcard or a string with a list, a set of variable names delimited by spaces, and then where it makes sense, the utility could operate on a whole set of tplot variables at once rather than having to write some kind of explicit loop. And so that wildcarding ability is now available where it makes sense in PySpeedS. So I'll go through a few concrete examples here. First up, I'll talk a little bit about the plotting combined variables in a single panel. So here's one case where that's helpful. So in this case, we have two different Themis instruments, one covering higher like MeV range particles, and then a different instrument captures the lower energy range particles down to like single-digit electron volts. So, so what I've done is I've taken a single time interval. The topmost plot is just the high energy data. The bottommost plot is just the low energy data. And then the middle plot is what you now get if you create a composite variable using those two pre-existing variables and then plot them on the same panel. And it's a little bit tricky because as you can see, when we make a plot like this, the color mapping is sort of adapts, based on what data ranges are actually in the data. So, looking between the two instruments, those are probably going to differ. And you don't want to get into a situation where you're trying to display two different color maps on the same panel, or like have multiple color bars. You really want to combine them and make them consistent in a single plot. And so now PySpeed is a lot smarter about this. You could do it before by sort of hand tuning like your Z range or Y range parameters but it was not very convenient and error prone. So now we do a pretty good job of sorting all that out before you actually make the plot. So now you can see on the middle plot, we've got actually both energy ranges represented, and we've sort of normalized the color map between them. And now what this buys you is you can look like you can see this feature here around 1500 hours, where it's sort of crossing over from one instrument into the data range of the other instrument. And then, putting them on a combined plot like this gives you a very nice sense of like how well the instruments are cross-calibrated to each other. So that's a very nice way to visualize it. And then another way you can use this is a situation like this, where in this case, this data is coming from the same instrument, but we have it at different time cadences. So in the upper, this is STEMIS data at what we call full resolution, which might be every minute or so you get a particle distribution function. And then down below, periodically we'll have intervals of burst data where we'll take a complete distribution every spin period, so about every 3 seconds instead of every minute. And again, as I mentioned before, when you look at the variables separately, the Z ranges, the color mapping gets sort of customized for the data range that's actually in that variable. And so you would not want to have these different color maps, showing up in the places where we have burst data available. And it's a little hard to see at this resolution, but please trust me when I tell you that this does actually incorporate the burst data, and you can see that it's nicely, the color maps are compatible, so it sort of melts away. But if you were to zoom in on it, you would see that the higher cadence data is still there. Let's see. This is an example. Let's see. Yeah, this is an example of what we call the var labels, where this is, I believe, some ERG data. And so we have some actual plots at the top, and then down below we're plotting, or not plotting, but just annotating it with some L shell values, magnetic latitude, magnetic local time. And we used to do that by adding a bunch of extra x-axes underneath, and then playing around with the tick labels to get those numbers. But as you can see, it's kind of distracting to have the extra axes in there, and it's not very compact. And so we've had a lot of requests to change that. So this is what it looks like now. We changed it so now when somebody asks for these sorts of variable annotations, the option is now there to actually create a separate panel underneath the plot panels. And then within that panel, we place annotations at the tick marks for the variable values. So this is a lot closer to what you would see in IDL. So that's what the users ask for, and that's what we now have. Yeah, so the interactive time selection feature, this came out of one of Vasilis's homework assignments for his class. So we had to scramble a bit to get that implemented so his students could use that. And the way that works is in a tplot call like this, we have this return plot objects parameter, a flag, and if you specify that, it returns the underlying matplotlib objects that are being created for that plot. So then we developed this seat time routine where if you call that on the plot you just made on that underlying plot object, it puts you into a mode where you're moving the cursor around on the screen. Here's an example. I didn't want to try to do a live demo, but hopefully this will get the idea across. This is cluster data from a magnetopause crossing. And then we wanted to get the times when each of the cluster probes crossed the magnetopause. So you can see I've made a selection here. So you click here and it, like, this green line is sort of the cursor, which moves around. And so I've placed lines here, and then in the next panel here, and then the next panel over here, and then the final panel over here. And you see that those lines have stuck around. So you have the feedback on what time selections you've made. And then you can cue on the keyboard or right click to stop the selection. And then what you get back is a list of Unix times in the output variable. And then you can use that list later on in your code. And like in this case, we took an average time for the crossing and then calculated some other parameters at that average crossing time. So we've also made some improvements in our analysis routines, especially in some of our custom coordinate transformations. So one feature we've had is what we call minimum variance analysis. So if you have, say, a magnetic field variable in, let's say, GSM coordinates, what you could do is sort of chop that time interval up into separate time windows. And then in each one of those windows, you could sort of look at the X, Y, and Z components of that data, and then form, I guess, a covariance matrix, which represents basically what you get out are eigenvalues and eigenvectors, and that gives you a direction along which the maximum variance is happening in that window's worth of data, and then an intermediate basis vector, and then a direction with the minimal variance. And so over your time window, you get basically a set of these basis vectors, and that means you can construct a rotation matrix so that if you want to put other variables into that minimum variance coordinate system, you could just apply that rotation matrix to anything else that's in the input coordinate system. So the new features here are getting the basis vectors and the eigenvalues out as separate outputs as opposed to just the rotation matrix. And then we noticed there was actually some we're seeing some strange differences between the IDL results and the Python results. And it turns out that there's an ambiguity in how you define the signs for this. So if the variance, it's not signed. So whether you're looking like, say, the plus Z direction or the minus Z direction, the variance is the same along that line. So in the output, if you're making a rotation matrix out of it, you want to have a right-handed coordinate system, which we were getting, but because of that sign ambiguity, it comes out that you could flip the signs on any two of those basis vectors, and you still have a right-handed coordinate system, and it's still valid. But it was sort of inconvenient to have this, sometimes be different. It makes it tough to test things when we get different results in IDL and Python. So basically what we've done now is imposed a sign convention on it to resolve that ambiguity. So the minimum variance direction and the intermediate variance direction now we choose the signs so that the Z component of each of those basis vectors is positive. And then that sort of uses up all our degrees of freedom. And then the maximum variance direction, ends up, whatever sign it needs to be to make a right-handed system. And after doing that, now we have very good matches between the IDL results and the Python results. And then we've improved our support for field-aligned coordinates. Again, so for your input in something like this, you're typically taking a magnetic field vector, and you want to set up a local coordinate system that has the plus Z aligned with the field vector. Now that still leaves 1 degree of freedom for where you put the X and Y axes of that coordinate system. So up to now, we've only supported really one choice you set this by specifying a reference vector to use. So that that might be, for example, radially outward from the satellite position, or radially inward towards the Earth, or you might take a reference vector that's aligned with, say, YGSE, or maybe just in the equatorial plane, or maybe aligned with the azimuth of where you are in the orbit. So now in the Python side of things, we've added full support for all those choices of reference vectors that were available in IDL SpeedS. And now, so the way that works is you take this reference vector, and the plus Z axis is defined for you. That's aligned with the magnetic field. And then you just do a couple of cross products with this reference vector, and that gets you the X and Y basis vectors. So now that works the same way in Python as does in IDL, and we verified that everything matches up nicely. So that's another big improvement. Let's see, Sean actually found a bug in our T wave pole routine. This is a wave polarization analysis tool. And it turned out when this has the ability to do frequency smoothing. So the wave polarization, you're taking this at a you're working in sort of Fourier transform space. So you have many spectral bins that you're working with, and we have the ability to sort of average through those bins to smooth things out in the frequency domain. And it turns out the way we were initializing that was non-deterministic. Like, I guess we were just taking whatever happened to be in that memory. And then if you have frequency smoothing specified, some bins might never get touched because they're because of edge effects. And so you would run the test one time and run it immediately a second time and get different results, which is no bueno. So Sean happened to notice that when he was testing the shared PyHC environment. And that was a real head scratcher for a while, but we did finally get to the bottom of that, fix that bug. So now we have deterministic results, which is good. We've also added better support for boundary normal coordinate transforms. So that's where you have one in your local coordinate system. You have one coordinate direction that's perpendicular to the magnetopause, and then the X and Y are you have maybe a few different options for how those get aligned. And what we've done, I think we had that feature before, but it worked a little bit differently. I think it only worked on Python arrays and not T-plot variables. So now we've made that interface consistent with the other tools like the minimum variance analysis and the field aligned coordinates, where you put in your input parameters, and then you get back a rotation matrix to put you into the new system. So that is now consistent with those other routines. We've gone through and updated anything that uses magnetic coordinates. We're now using the IGRF 14 coefficients that were just released this year. So that's fully updated now. And then in the MMS particle routines, we now support doing bulk velocity subtraction when you're generating spectra or moments from FPI or HPCA 3D particle distributions. And this is a big contribution actually by one of our summer school students, Anansa Keaton, and she contributed some key code. So shout out to her for bringing that improvement to PySpeedS. So here's an example of that. The top and bottom panels are reference data that we've generated in IDL. Top panel is without the bulk velocity subtraction. Bottom panel is with bulk velocity subtraction enabled. So you can see we've taken out a lot of that very narrow range of velocities, and so that's more what you'd see if you were like moving in the plasma stream with the bulk flow. And then I'm all running out of time here, but I just have a few things I'd like to say about the load routines. We have a bug fix for MMS FPI data. We're getting multiple copies of the data in the same variable, and that turned out to be because those variables actually occurred in multiple data sets. We were trying to load them all at the same time, and we didn't account for that possibility. So that's now fixed. We've had a few user contributions for additional data types that are now supported for Wind, RBSP Maven, and I believe MMS. For Omni data, again, this was something we did for consistency with IDL SpeedS. We defaulted to the HRO rather than the HRO2 data set. The latter is more processed, but it's also more prone to gaps. And that was causing some confusion. So we changed the default to be the less gappy version of the data. A few of our data providers have updated their URL structures. So PySpeedS has been updated for the new URLs for Akebono, for some of the NOAA, GOES and POES satellites, and for the ESA and Korean Space Agency's CompSat, geosynchronous satellite. We had a few users that got confused. Like if you had installed a minimal, like stripped down version of Python that did not have tkinter support, you could get some confusing diagnostics if you tried to use the load via CEDA-web functionality, which depends on tkinter. So that's been beefed up a bit. We now do a better job of detecting that and telling the user what went wrong. And then internally, we do a little bit better job of handling like if the web server on the other end sends you gzip compressed data, we now detect that at the time of the download and uncompress it rather than having to like add code, like that data. It might not be just a CDF or a net CDF. It could be just ASCII, or it could be a CSV file, and you don't want to have to make that check in a million places. So we check for that now in the download routine, and so centralize that handling. And finally, I'll mention, especially from the summer school and the class, that prompted us to really step up our game in terms of documentation. So we've cleaned up a lot of the plot documentation, removed some obsolete options that didn't do anything. We've added a bunch of options that were missing and grouped them in the documentation by category to make them easier to find. And then we've added documentations for a lot of things that were previously missing from our Read the Docs pages. Oops. So here's a screenshot of some of the plot documentation, how it looks now on Read the Docs. So you can see now we've broken this up, like y-axis options or error bar options or marker symbol options. Now we have a table of synonyms. So the left-hand column shows, if you were looking through the code for that feature, that is the name you would look for in the code. And then for each of those, we give the accepted synonyms that people are able to use for it. We've really beefed up our new user getting started guide, and we really walk them through every step they need to use PySpeed as, from installing Python to installing an IDE, setting up the environment for running PySpeed as, and then we give them a simple PySpeed as workflow to test, and we describe how to work with Jupyter notebooks. And I'll mention PySpeed S 2.0 in a bit, but we have a migration guide for how to update user programs for when that transition happens. So we really, you might say that a lot of this stuff about, like, say, setting up PyCharm or setting up an IDE, why duplicate that effort? But what we found is, like, users really, some of them may want to choose their own adventure and, use Visual Studio Code, or they have some other tool that they prefer. But for somebody who just wants to, like, okay, what do I need to do to start using PySpeed as? It's helpful for them to have all this in one place, even I duplicate some of the information on python.org or the different IDE documentation. So it really helps that, we really highlight, okay, here's where these controls are when you bring up your IDE, and these are the steps you have to take to run a PySpeed as program. And so we've had good feedback about this. Our users are happy about having some really detailed instructions. And then for the future, we've been saying this for a while. We think we're getting close to putting out a PySpeed S 2.0, and the biggest change is that the PyTplot package is going to be merged into it. Right now, that's an external package, and there's actually a couple of different versions of it floating around, and that's been very confusing for our users. It's very easy for them to try to do a manual update and then end up installing the wrong version, and then suddenly PySpeed S is broken and nothing works. And then the other big change has to do with importing project-specific modules. The old way is you just imported from PySpeedas.mms, import FGM. We've introduced a new level just to keep the project-specific stuff in its own set of modules. So in the future, the second way, from PySpeedas.projects.mms, import FGM, that will be the way to do it going forward. We'll remove these backward compatible hacks that we've had in there for a while. And most of our documentation and tutorials already cover show the PySpeed S 2.0 way of doing things. So hopefully we're ready for that. And then some other features we intend to implement in the future. So better support for non-time series plots. We want to improve our support for GeoPack magnetic modeling routines, better support for field line tracing, and we might want to look into using, or at least allowing the use of SpacePy or Komodo, which have their own magnetic modeling capabilities. So that's something we're looking into. So again, the sort of non-time series plots, this is one from PyHC Summer School that we used. So this is an orbit plot of a few missions with magnetopause boundaries plotted on it. This is I believe, cluster, or maybe MMS. Anyway, a formation plot showing where the the 4 satellites were at a moment in time. And then we've plotted a few vectors on top showing a few attributes that we calculated that crib sheet. And then this is a hodogram. This is actually from one of Vasilis's assignments. And we've taken a magnetic field vector and projected it onto the minimum variance, actually the IJ plane in minimum variance coordinates. And you can see this is kind of interesting. It starts off as sort of elliptically polarized in this direction, and then it mode converts, and you end up going, the polarization is in the opposite direction for the latter part of the wave. So I thought that was interesting. Anyway, that's all I have. So hope you all enjoy those changes. And as always, we're eager to hear from our user community, and we're happy to try to implement any suggestions that people come up with.
Thanks, Jim. Really nice and comprehensive overview of all the changes that have happened. Y'all have been hard at work. Any quick questions for Jim before we move on to the final talk for today, the tutorial actually? Go ahead, Dan.
Hey Jim, this is Dan.
Hey, Dan.
Great talk. I was wondering because I'm genuinely curious. What is the difference between like the maximum variance analysis that you described and something like principal component analysis?
I'm not sure, to tell you the truth.
Okay, be happy to talk later, maybe.
Yeah.
Great. Well, in the interest of time, we're going to go ahead and move on to the next tutorial. If you have any questions for Jim or anyone else, they're still on the line, feel free to throw this in the chat.
Thanks. And I will attempt to share my screen. Hopefully the universe doesn't explode again. Cool, I think I'm still here. So, yeah, I just updated my operating system a week or two ago and occasionally get like, you have to log out now error messages. So if that happens, I'll be back in like 85 seconds. Time me. So what we're going to cover, we're going to switch gears a bit and talk about UV, which is a new tool that has been making waves across the Pythoniverse. And what UV is a new Python package installer and manager written in Rust. And because it's written in Rust, of course you have to say that it's going to have like excellent performance, and it does. And because of not just the performance, but also the usability and the community, UV has seen like really rapid adoption since it was released less than a year and a half ago. So I put a link in the chat to the installation instructions and to this file. So if you want to follow along, please feel free to install it and open a terminal or PowerShell. And once you've done it, you can do UV self update and make sure that it's on the latest version of UV. All right. So why UV? For those of us who have been working in Python stuff for the past however many years or millennia, we've probably noticed that the Python packaging landscape is kind of fragmented. And part of that is because Python's like 30 years old, over 30. And newer languages like Rust have tools that provide a more unified experience. And so Astral, the company which is shepherding the development of UV, is working to create a unified tool chain for Python using tools that are written in Rust, so you get excellent performance. And there are a couple of techniques that UV uses that really help make a lot of these improvements. So UV does an excellent job of caching packages and registry information so it doesn't end up needing to be re-downloaded. Dependency resolution by UV is incredibly fast, especially if the cache has been is warm. So this is one benchmark where they install the Trio package with a warm cache, and UV does it significantly faster than all of the other available tools. So once you start using UV, all the other tools seem a lot slower, and it really helps including UV in CI because of the performance, and it helps you get results from tests and things like that faster. Right. But UV, it's not just performance. UV has other capabilities, like it has an option to resolve environments for the lowest allowed versions of either all or direct dependencies. And this makes it a lot easier to test that our minimum dependencies of packages are actually the minimum dependencies. And like we can find out if new changes lead to errors or things like that. And there's also an option to solve for an environment using only releases made up until a certain date. UV also has a universal lock file. And one thing to note about requirements.txt style files is that they don't always work across different operating systems or versions of Python, unfortunately. But UV lets us create a single lock file that fully defines an environment for multiple versions of Python, multiple operating systems, and all dependency groups. For Plasma Pi, we lock dependencies for running CI, and we went from like 18 requirements.txt style files down to a single UV lock file. So it was a huge relief, reduced a lot of clutter in the repository. One thing to note is that there was a recent Python enhancement proposal that defined a pylog.toml standard as the next generation of requirements.txt files. And UV is compatible with pylog.toml, but the UV log files have more features to help with dependency resolution. And so, I still recommend using uv.lock for things like CI. Another important thing to note is that Pylock would be a great name for a supervillain from a 1980s children's cartoon. So if anyone is planning to go back to the 1980s and do that, I highly recommend it. All right. So we'll start off by creating and managing Python virtual environments. And if you haven't heard of a virtual environment before, it's an isolated space where we can work on our Python projects separately from our system installed Python. And this really helps us keep things organized, because if we install stuff to our system Python, that can end up leading to a really messy situation and dependency conflicts and all wonderful excitement. So I'll move on to the live coding part of this tutorial. And I always like to mention that a quote about doing live tutorials is never do live tutorials, but hopefully this will work all right. So I'm going to start by creating a directory, UV tutorial, and entering it. So that will make it easier to delete this afterwards. So let's start off by using the which command in Unix to see which version of Python we're using. And in this platform, we're using the system Python, user bin Python. So let's start by creating a virtual environment. And the commands for this are pretty similar to other tools, the env and virtual env. And for all of these, we can precede it with UV. So let's do UV, venv, and then we don't have to include this, but we can include Python 3.13, so the newest version. And I did that really quickly because I've already done this. I've already downloaded this version of Python. And if you're following along, it when we created a virtual environment, it has a command to say activate with, in this case, source, the location of the activate executable. So we'll need that in a bit, and this will be different for different operating systems. So let's start by looking at the contents of the directory. So ls-a to show everything. And there's now a .venv directory, which contains the information for the virtual environment. It doesn't contain the packages themselves, I don't think, because those are located in a cache, which is elsewhere. All right. So let's check which version of Python we're using now. And though we created a virtual environment, we're still using the same version of Python because we haven't activated it. So I'm going to use this command, but for other operating systems or PowerShell, there will be other commands that will activate it. Source.venv/bin/activate. And I'll move this over a little bit. There, almost. All right. And so if you're using PowerShell, you might need to run this as an administrator or in administrator mode. So let's see which version of Python we're using now. And I'm just going to decrease the font a little bit. Is this still okay with folks? Or let me know if it isn't. All right. So now we've went from using the system Python to the Python that is defined in this virtual environment directory. So we've activated the environment. But if we close this terminal, we would need to reactivate the environment unless we do something like add a command in our shell configuration file, like for bashrc for bash, and that would let us set up a default virtual environment that gets activated whenever we open a terminal. Installing packages with UV into a virtual environment is very similar to using pip, except that you precede it with UV. So UV is a drop-in replacement for pip. So let's do UV pip install numpy and hit enter and resolve one package in 364 milliseconds. And so we now have an environment that contains numpy. If we want to deactivate the environment, we can use the deactivate command, executable, and now it's deactivated. The name of the environment is typically prepended to the prompt in a terminal. All right. So now that we've gone through virtual environments, we can go through and create a new project with UV. So we can do UV init, put a space there, and let's call it my project. And it says it initialized my project at this particular subdirectory. So let's do cd my project. And then let's see what's in the directory and using the -a to show all the files. So UV init ended up creating a bunch of files, including a .git directory so that it initializes it as a Git repository, though it hasn't actually committed anything yet, I don't think. A git ignore file, a Python version file, which is primarily 3.13, an initial README file, a main.py file, which is the script, and then a pyproject.toml configuration file. So let's take a look at pyproject.toml for what UV auto-populates. And let's use the cat command, short for concatenate. So cat pyproject.toml. And UV added a bunch of initial metadata and name of the project, version. We could change this file to have a description, a short description of it, reverse Python, and so far we don't have any dependencies in it. Right. So let's take a look at main.py. So cat main.py, and it has an initial main function, and then under the if name equals main block, it calls the main function. And so what's happened here is in this block is what happens if the file is run as a script. But this will not be run if the file is imported. So if we create a main function from creating a main function that's separate from what's included down here makes it helps out a lot with the organization and makes it so that we can run main when we import it from Python rather than having to like run it as a script. All right. So let's run this. We can do this in this case with our system Python, running main.py, and it says hello. But since we're using our system Python, if we ended up having to depend on NumPy or AstroPy, then we would have had to like manually install them prior to running Python, and that can lead to dependency conflicts and things like that, and user errors. But if we use uv run main.py, it will take care of all of the installation of packages for us. So it'll create a virtual environment and run main.py using that virtual environment. And we can do ls-a again. And in the directory, there's now the .venv folder and also uv.lock, which is the lock file that defines the environment contained within .venv. So if you've used pipx before, this is similar to that. So we can add dependencies also. So let's say uv add astropy. For example, if we wanted to use astropy.units to write a cookbook using units like Bard megaparsec. Not that that has crossed my mind a billion times. So it resolved the environment very quickly and installed astropy. So let's now see what's in pyproject.toml. And lo and behold, astropy, the most recent release of astropy, is included in as a dependency for the project. And when we did uv add, it also updated the virtual environment and the uv lock file. So it handles all that for us. If we wanted to add a specific version of a package, astropy, we can do 7.0.1. And it'll do this pretty quickly. And then if we can do cat pyproject.toml, and it says astropy equals 7.0.1. It's also possible to add and remove packages. So we can do uv add sumpy and very fast resolution, and then uv remove sumpy. That's also very fast, 10 milliseconds to do the re-resolution. All right, I do have a bit more time. So far we've created a Python project, which is essentially a script associated with a pyproject.toml file. But for PyHC projects, we generally want to create a package instead. So I'm going to go up a directory, so cd dot dot, and then I will clear it. Let's do uv init and call this my package -- library. And it initialized a project my package as a library. So let's enter this cd my package, and then ls-a to see what's in there. And it's mostly the same as above, except that there's now an src folder, which contains a do ls src, and src contains a my package directory, which contains the source code for the package itself. The src layout has become the more recommended strategy for structuring Python packages, as opposed to having a top-level directory, which has the name of the package. And there are a couple of reasons for that, which I can share some resources if you remind me later that go into it. All right. So let's do ls-a and then src my package. So in the src my package directory, there's an init.py file, so that makes the directory importable, and also a py.typed file, which is an empty file, and it denotes to type checkers that this package has type hint annotations. So it's helpful to do for all of our projects if we use type hint annotations, which are very helpful. And it does help downstream packages also. All right. So let's create a virtual environment for this package. So UVVNV Python 3.13, I think that's a typo. And let's activate it. And this command will be different for different operating systems as before. So it's the command that gets printed out here. And so I've now activated the my package virtual environment, which is the in.env in this file. So now we can install it with uv pip install -e dot and it resolved the package and built it and installed it. So in here, the -e makes the package installation editable, so we can change the package without having to do uv pip install again. Let's open Python. And now we can do import my package and my package .hello. And we're good. So that's it for the tutorial. I'm happy to stick around for a bit after. Now exit Python. Turns out for Python 3.13, you can type exit without having to do the parentheses. Exciting new feature. It's good to update to the newest versions of Python for our work. And also, thank you all for being wonderful people. I'm done. So any questions? I don't have the chat showing up for me.
I saw in the chat. Thank you also for being a wonderful people as well. Do we have any questions or comments for Nick?
Well, I just have to comment first, if I can, that speed alone was just incredible to watch. I mean, we recently switched over to the PyHC environment to use Mamba instead of Conda to install some things, and that was a pretty big speed improvement. But now I feel like I have to look into UV after I've seen that.
Let's maybe we can do a quick unscripted demo. So uv pip install, and it's like PyHC core.
Yeah, PyHC-core. Oh
Oh
yeah,
wait, I think that's like older Python, right? Okay,
Because
I'll cancel that. But
yeah, that's a good couple minutes with pip. And is that finished already there?
no, I canceled it.
Oh, you can't. Okay,
Oops,
yeah,
because I want to do, is it 3.10 or 3.11?
11.
Okay. So source. And then all right, so the package resolution resolved 212 packages in 284 milliseconds. And I think that's because the cache was warm, because I tried this command just before. So how long did you say this took, Sean?
It was at least like 2-ish minutes when I was pip installing it, maybe 3.
Okay, so the package resolution was really quick. It did have to do some preparation and some installation stuff because this is a pretty large environment. But the performance it's incredible. It's hard to go back to other tools now.
And then just one more question before I cede the floor, because I have to. Do you know if it resolves dependencies any more intelligently than Conda does? Like, I know Conda is smarter at resolving dependencies than pip. I'm wondering if UV is even smarter than Conda.
I don't know. They have been putting a lot of effort into their dependency resolution, and I think they actually use a different tool under the hood, which the documentation might show.
Well, but don't worry about it. I'll Google that on my own later. Thanks for everything.
Thank you too.
Isaiah, you have your camera on. Does that mean you have a question?
Oh yeah, I just wanted to kind of say that like I was also very impressed with the speed after using pip for a long time, and it kind of reminds me of like making the switch from npm to esbuild, which is also built with Rust, and even the interface of interacting with through installing packages is very similar. It seems like the sort of esbuild. So I'm not sure if that was like something that you kind of based it off of, but it seems similarly impressive, and I'm also interested. I'm gonna check it out now. So thanks, awesome demo.
Thanks. Yeah, it's really worth checking out. They developed it inspired by Cargo from Rust, which might be similar to like the same general philosophy.
Mm-hmm. Cool.
Any other questions or comments? Great. Thanks again, Nick, for giving us tutorial.
Cool. Thanks.
All right. Well, that's all we've got for today, folks. We'll be back again tomorrow for some S3 awareness and high-speed S chat. So Jen will be coming back for that. Cloud catalog updates from Sandy, as well as a good hour chunk of discussion with Sean. Tech lead
Promise to have
projects.
interesting things to talk about to fill an hour.
I'm excited for it. Great. I'll see you all again tomorrow, same time, same place. Thank you.
Sweet, thank you.